Great. Thank you so much for having me. Sorry I couldn't make it in person. I would have much preferred, but couldn't make it this time. So I'm going to be giving an overview of some work that is joint with Ricardo Carretero-Gonzalez, Peter Schmelcher, and Panos Kevrekidis, who's here today. First, let me start with the model and just the coordinates and the setup. We'll be looking at the torus here, and you'll see me switch back and forth for different coordinates, but for the moment, theta represents the poloidal coordinate going sort of around the circular tube of the torus, and phi represents the toroidal going around the length of the torus. And take notice that theta equals 0 corresponds to the outer circle of the donut, and theta equals pi corresponds to the inner.
No.
Oh, I got muted somehow.
Okay.
All set?
Yes, thank you.
Okay, sorry. I'm not sure how much you missed here, but looking at the torus here, we have theta equals 0 corresponds to the outer equator, and theta equals pi represents the inner equator. And we'll be looking at the nonlinear Schrodinger model, in particularly the defocusing case with the minus sign. And we'll be looking on a torus background. And here, if you take a look at the Laplace-Beltrami operator that we've got here, a couple of things to notice is that we have translational invariance in the phi direction, and in these two special areas of theta equals 0 and theta equals pi for the inner and the outer equators of the torus. What happens there is that this term drops away in the Laplace-Beltrami operator. So we will see some special features that arise on the inside and the outside of the torus. Like I don't, or maybe you didn't hear me say, I may be switching back and forth between different coordinates throughout the presentation. So in addition to the toroidal coordinates of theta and phi, you'll also see the isothermal coordinates of u and v. And here's the transformation in between those. And the isothermal coordinates in particular correspond to a metric that's conformal to Euclidean with a scale factor. So first we'll start with looking for dark solutions, and particular we'll look for stationary solutions. So we'll just remove the time dependence by multiplying e to the minus I mu t. So the mu here is the chemical potential or the frequency, and what we'll be doing is looking for solutions as a function of both the frequency, but also the ratio that I'll be calling alpha, which is the small radius of the torus divided by the big radius of the torus. So the small radius being sort of the radius of the thickness of the donut, and the big radius is the wideness of the torus. So you'll see throughout the presentation is solutions will be represented as a function of mu or as a function of alpha, perhaps for a fixed mu or for a fixed alpha or vice versa. And most of the figures that you'll see in this presentation are for r is equal to 12, but they're very similar for other radii. So first, let's focus on the stationary solution, which is equation 2 here, where the time dependence has been removed. And we'll just look for stationary solutions using Newton's method. But what I'm going to do is I'm going to run through all of the different criteria and elements that you need to, excuse the train, of course, train comes at the perfect time. So first, let's look at just the basics of if you're going to put a vortex on a torus, what kind of considerations do you have? So of course, if you have a square box and you're identifying the left and the right boundaries and the top and the bottom boundaries, what you can see from this figure is that if you had a single vortex alone, like you can see on the left side of the screen here, it's just not going to work. The left and the right boundaries will not match up, and as well as the bottom and the top. So what we'll see is that in the torus, we will need to have an even number of vortices, similar to the figure on the right, in order for the matching to work out on the left and right and the top and bottom boundaries. In addition to an even number of vortices, we'll also have, we'll take a look here at the background amplitude of the vortex profiles. In the Thomas Fermi limit, where the derivatives are equal to 0, you can just see it here, that the magnitude will be square root of mu. And then each individual vortex will be modeled by a hyperbolic tangent function in order to represent the core amplitude of the vortex. And as you can see here, I've just plotted it in one dimension, but of course the torus, it's a two-dimensional version of this, is that when we've got the mu in here, as mu starts to increase, the width of the torus starts to shrink to 0. And what we get is that as mu goes to infinity, the width of the vortex goes to 0. And that brings us to the point vortex ODE model that we're going to show in the next couple of slides. So first, defining the complex coordinate. The isothermal coordinates were u and v, and so we're combining the isothermal coordinates together into u plus iv for the complex coordinate. And there's previous work by Gunther, Massignan, and Feder, where they have explicit formulas here for the phase profile of the vortices. And you can double check the periodicity. We've got the Jacobi theta function, and it's also, of course, periodic in both directions. So in the reduced ODE model, in the point vortex model, each vortex experiences the velocity given by the gradient of the other vortices. And using this phase profile here, from Feder and collaborators, you have this expression for the velocity in the reduced ODE model. So looking at just the ODE model, this here is a plot of the velocity that you see in the ODE model. And now I'll start to differentiate between the different types of solutions that we're going to be looking at. The first type of solution is the vertical dipole. And you might wonder what vertical means in this situation. So let me just go back here real quick. So basically, if I say anything about horizontal, that means that it's going around in the poloidal direction. And if it's talking about vertical, then that's going around the thickness of the torus instead. So looking at the reduced ODE model and the velocity here, we see that there are points where it's unstable points here, where we have the solutions for the vertical dipoles. Now, this is just the ODE model. I'll get into the PDE model as we go along. Quite similarly, we're looking at the dipoles here. So this is with just simply two vortices. This is a lot more interesting of a phase profile here. And what we can see from this picture is that for the horizontal dipoles on the torus, the outermost, on the outside of the torus, they're stable. And on the inside of the torus, you can see over here on there's little plus signs here indicating the horizontal dipoles on the inside of the torus, and these are unstable. Now, everything that you see here is mostly from the ODE model, but except for these thick lines, the thick lines of the green and the purple here are the trajectories that we matched from the PDE model. And in addition to the considerations of having an even number of vortex, making sure that the background density is correct, modeling the core of the vortex by the tangent functions, you can also introduce extra windings where the phase profile winds around an extra number of integers, and you can get additional solutions there as well. So all in all, the stationary solution can be obtained with Newton's method, and you have to put all of these components into your initial guess to the Newton. You have your background amplitude according to the Thomas Fermi limit. You have the vortex core amplitude according to the tangent functions. We've got the phase profiles that are according to the Fedor equations. And then we have the actual locations of the vortex that we can use pulling from the ODE model. And then, of course, you can build in the extra windings optionally. Okay, so let's look at what we have for solutions. This is a set of pictures of the so-called vertical dipoles here with alpha equals 0.4 for the top row. And what is shown is that the top row is just the amplitude and the second row is the phase profile. And similar down below for alpha equals 0.7, remember alpha was the ratio of the small radius to the big radius. So alpha equals 0.7 just corresponds to a fatter torus. And again, here the amplitude is shown in the third row and the phase profile is shown in the fourth row. Again, we can get additional vertical dipoles by incorporating those extra windings. And this is what they look like when you incorporate a couple of those extra windings. The extra windings can also affect the stability. There's a sort of delicate balance with the stability of the force of the opposing dipole together with the winding. Okay. Here are some pictures of the horizontal dipoles. Alpha equals 0.4 in the top set of panels and alpha equals 0.7 in the bottom set of panels down here. And here we have the horizontal out as compared to the horizontal in. These are all solutions to the stationary equation for the PDE model. And again, you can incorporate the extra windings, and what they do, if you look at what the effect that they have is the horizontal dipole will still be a horizontal dipole, but they might be located with respect to each other in a different configuration slightly. And I forgot to mention previously, but these little boxes here are the approximation from the ODE model for what is predicted from the ODE model to be the location of the vortex solutions. And the actual solution that you see plotted here is from the PDE model. So here we're seeing a very good agreement between the ODE model and the PDE. And finally, we have what we're calling the diagonal dipoles, where they're just slightly offset from each other. And aside from just happenstance, where your Newton just converges magically to something, as you're kind of messing around with it, you can also do a systematic search of the velocity equation back here from the ODE model. You can reduce it just to the diagonal situation where they're offset from each other in exactly the sort of off-symmetric type of configuration. And you can search for the locations where the velocity is equal to 0. Oops, I skipped over it. Okay, so yeah, we've got the diagonal dipoles here. And the diagonal dipoles will exist again for a big range of alpha and mu values. Now let's take a look at the stability and the dynamics. Here's the standard equations for monitoring the stability. And what we can see here is that in this particular situation, we've got the horizontal in is generally unstable and the horizontal out is generally stable. And we saw that from the phase profile pictures a couple of slides ago. We also have the diagonal dipole over here, which is generally unstable. And here we have a vertical in that this one just happens to be stable. If you build in extra windings, it may or may not be stable for different types of configurations. But again, what we can see here is that as mu goes to infinity, there's you can see that the PDE stability results are notated with the blue lines, and the ODE is represented with the black line. So you can see that as mu goes to infinity, well, infinity, you don't have to really go very far in order for them to match up. Here we're only at mu is equal to 5, and there's a pretty good match between the ODE and the PDE results. Okay. So the stability results that this is the continuation for a fixed alpha continued in mu, where you can see as mu gets larger, the correspondence between the ODE and the PDE results. Here, this is just for mu is equal to 5, continuation in alpha, and you can see a very good correspondence in between the results here as for all alpha values, as long as the mu value is pretty high. And again, we have these little boxes represent the results in the ODE model, whereas the actual solution that's plotted here is from the PDE. Okay, so let's take a look at some of the dynamics. As you can see here, there's 2 examples down below of the horizontal dipole in. And what happens for the dynamics is that as they move forward, they stay horizontally aligned, and they'll either go around the torus or they'll just oscillate back and forth. As you can see on the left here, these are not, maybe I don't know if you can see that they do not touch. So they're not going fully around, they're just going around and coming back. And you can see those example dynamics also in the phase profile, from the ODE model. The diagonal dipole the example dynamics will look something like this. They'll start translating in both the poloidal and the toroidal directions. And finally, the dipoles are what we did in quite a bit more depth than anything else. But as I said in the beginning, the number of vortices just needs to be even. So you can easily do a study. We've only gone as far as to just study the quadrupoles, but you can also study, a higher number of vortices. What I'll show you here is the quadrupoles, and then I'll show you some dark stripes as well. So the quadrupoles, again, what you can do is go back to that ODE model. You can reduce it to the quadrupole situation, and you can do a systematic search of all of the possible quadrupole positions here and find where the velocity is equal to 0 and where there's a predicted solution. So again, these are results from the PDE, and you can see that the matching from the ODE is with these little square boxes. And we see a very good match between the ODE and the PDE. We've got some stability noted down below. By the way, the ones that are plotted here are the quadrupoles numbers 1, 2, 3. And for those in particular, or I guess for 1 and 3 in particular, if you look at the stability down below, there is a stable window for the quadrupole number 1, which is the aligned quadrupole. And there is a small stable window in a tiny little portion here. If you zoom in quite a bit, there is a small window of stability for these ones as well. And finally, if you look at the bifurcation as a function of mu, and this one in particular is for a fixed alpha is equal to 0.7, you can see the branches bifurcating, and the horizontal, a dark stripe situated horizontally around the torus will bifurcate into the dipole. And here is a quick showing of that bifurcation here down below. If you follow ABC DE, you can see that the solution kind of separates and the vortex solutions start to form. Okay, so finally, let me just show you some dynamics. This is one of the dark stripes. And as we move forward in the T variable, you'll see that it starts to break. Oops, I'm pressing the wrong button. It starts to break up into individual vortices. And then those vortices will have some sort of combination of toroidal or poloidal motion. In this particular case, they start going around poloidally. And here's another example where the stripes are in the other direction. And as the dynamics start to go forward, you'll see that they break up into vortices. And this one, one pair of them starts to fly around poloidally, while the other one seems to sort of stay put. Okay, so that's it for my presentation. Thank you very much. Any questions?
And we may have some question, yeah, Mark.
Thank you, Jenny. So the stability calculations that you did were essentially two-dimensional, right? You didn't allow for three-dimensional perturbations. Is that correct?
Correct, just as a function of alpha and mu. Mhm.
And
In
do
other words,
you-
for a specific alpha and specific mu.
right, but do you expect that if you were to allow for variation in the interior of the torus, that there would be some additional instability mechanism?
I mean, I didn't do those calculations, so I don't really have a sense for it, but I'm sure that that would be a really interesting, thing to explore. But it's not calculations that we did in particular. But there certainly is a constraint going on here with only allowing it to move around on the surface as opposed to the interior.
Thank you.
Can you hear me?
Yeah. Mhm.
Oh, okay. So yeah, I'll just repeat the question because the microphone was off. My question is about just the nature of the interactions you have in the point vortex model, because you're sort of solving the point vortices on a torus, and I just wasn't clear how the interactions on sort of the curved background differ from the planar case.
I'm not sure I actually understand your question.
So you presented the results from a point vortex model, and typically the point vortices have like a logarithmic type interaction, if you write the Hamiltonian, or a 1/r interaction in 2D space. But because you're on a torus, I'm just trying to understand, how does your point vortex model differ now? So you probably presented the equations at some point and I may have missed it.
Right. I mean, I don't have them here to do a direct comparison, but this is I don't have exactly the equations that you're looking for, but this is the velocity model. Yeah, none of these, I don't think any of these equations are exactly what you're looking for, because I don't have exactly the yeah, but I'm not sure at this moment.
Okay.
Maybe
Yeah,
I can comment.
yeah.
Yeah, so the logarithmic potential is still there. In fact, you can see it on this slide in equation 5. There is something logarithmic with the Weierstrass functions, and that involves essentially the potential of interaction of the vortices. So there is still that logarithmic term, but the problem is, it needs to live on a curved background. So there is this lambda factor, this kind of scale factor that accounts for the essentially the curvature of the background, and B, you need to account for the periodic boundary conditions. So you need to account for all the image charge vortices that effectively come from the periodic boundary conditions. So these are the two kind of additional things that add terms to the equation, but that logarithmic potential is still there. And in fact, it's in this expression for F that you see in here. It's kind of buried in there.
Okay, because it's interesting to have this model, because I mean, people have looked at this statistical mechanics of large numbers of point vortices, and so if the interaction differs now, it'll be interesting to understand the equilibrium properties of a large number of vortices on a curved background.
Heider, is that you? Yeah, so
Yeah,
I
that's
think
me.
yeah,
that's
so
me.
that's certainly a very interesting question. So since these equations were only written relatively recently, I think that aspect of computing partition functions and doing stat mech of vortices on these curved backgrounds would be a very interesting question. I completely agree.
Okay, right, thanks.
Thank you.